Hi everyone, welcome to today's webinar. My name is John Place. I work at Tulip, where I write about technology and manufacturing. I'll be the host of today's webinar, and today we'll talk about worker augmentation, the augmented worker in manufacturing. And so the point of today's webinar is to acquaint you with the idea of augmentation, give examples of how digital technologies are augmenting workers, and show why augmentation is necessary in today's factories. If at any point you have any questions, please send them in. If you need clarification on anything, let us know. After the webinar, we'll answer all of your questions and we'll circulate our answers to everybody who's registered. So please do be in touch. I expect the webinar will take about 20 minutes. So without further ado, let's jump right into it. So today's webinar will answer the questions: what is worker augmentation? We'll look at the different tools and technologies that are being used to augment workers. We'll look at more generally what a definition is. We'll look at why manufacturing needs augmentation in this particular historical moment. And so here we'll survey some of the broad trends in the industry. We'll look at technological development, and we'll talk about why augmentation is an important solution to the particular skills and labor and work conditions that manufacturing has at the particular moment. And then we'll talk about how augmentation can keep your operations competitive. Here we'll switch directions from the more conceptual things into the very concrete, on-the-ground realities of it. We'll look at some use cases. We'll look at some of our customer cases so we can show you ways that this is being used by real manufacturers right now. And then some of the ROIs that people are seeing from augmentation. So, what is augmentation? At Tulip, we define augmentation as any external, integrated, or assistive technology. And so this is kind of a complicated definition for just such a few amount of words, but I think we can break it down into something really simple. So by external, we mean that it isn't biological. It's technology that works outside of and around humans to improve their work within their environment. By integrated, we mean that it's integrated into a worker's context. It could be part of their workflow, it could be something they wear, something integrated into their clothing, or it could be something like computer vision, which is a sort of a more ambient thing, where it monitors what's happening in a particular area and responds to it in real time. It's interactive. So whether or not it's something that you're physically touching or that is sort of recording visually and analyzing a context, all of those are examples of augmentation. And so it's important to note that with augmentation, the goal isn't to replace workers. Humans are central to manufacturing. They're going to remain central to manufacturing for the foreseeable future. So augmentation acknowledges this reality and works to make people on the shop floor better at what they do, more efficient, producing higher quality. And it's about integrating workers more seamlessly into their environment. It's about creating systems and work environment that allow workers to be the best they can. And so another way of defining augmentation is that augmentation involves work. And the idea here is that when you introduce specific digital technologies into a workstation, eventually the nature of work done there is going to be slightly different. That in using the technology, it's going to change what workers are able to do, and therefore the tasks they're doing are going to be slightly different. We'll go over some examples of why this is the case and how this is the case later, but I wanted to flag this up front. So what are the values of augmentation? So the first and I think the most important is that it assists workers to achieve optimal performance. It works with them, boosts them, and quite literally augments what they're able to do. Because augmentative technologies are digital technologies, they're constantly collecting information, storing data, responding to things in real time, which means that engineers and manufacturers have much more data to work with. It allows them to sort of make decisions on a much more granular level, to respond to changes faster, and to iterate their processes much more rapidly. And it enhances human and machine collaboration. So one of the facts about the quote-unquote digital factory is that humans and machines are going to need to work together to be optimally efficient. There are certain aspects of manufacturing that are automated that humans are going to need to work alongside. So the idea of augmentation is that it takes the best of both worlds. It takes the things that sort of automated machines are best at and puts them alongside what humans are best at, and then together the most value can be created. So a synonym for the augmented worker that you've probably heard is the connected worker. And I want to explain a little bit what I mean by that and why it's important to think of these this way. So on the modern shop floor, the actions of workers are creating information as they go through whatever it is they're producing, whatever it is they're assembling. And machines are generating information as they work. With modern machine monitoring solutions, we have more machine data than we've ever had at any point in history. And so new digital technologies are able to interpret both streams of information in real time and respond to them. And you wind up with that dynamic shop floor in which humans are capable of responding to the signals from machines, and machines are capable of responding to signals from humans, and vice versa. And the idea of augmentation, or one of the ideas behind augmentation, is that in having all of this information and in having tailored responses moving back and forth between the sort of human and machine domains, the shop floor, much more sophisticated and much more accurate decisions will be able to be made on a much faster time scale. And another point I'd like to flag up front is that augmentation in manufacturing is a much broader category than just simply augmented reality. I think if I were to ask you before this webinar, or even possibly right now during this webinar, what is augmentation in manufacturing, many people's minds would go directly to augmented reality. It's a really attractive technology. There's really interesting use cases. But the big point I want to make here, and this is, I think, one of the largest takeaways I want you to leave with, is that augmentation encompasses a really large array of technologies and a really large array of use cases, only some of which are AR. And so later in the webinar, we'll go over many more of these in detail. And I think another myth that it's important that we talk through at this point is that the augmented worker isn't necessarily just an augmented operator. We're really not just talking about operators. And I think I'm flagging this is because when you Google augmented worker, you get 3 pages of Google results for operators, but that's not really telling the whole story. It begs the question, can process engineers be augmented? Quality engineers, managers? And the answer is yes, any manufacturing worker can be augmented by technology. And I'd suggest that the greatest gains can only be achieved when all shop floor workers are outfitted with the tools they need to evolve their work. And so we're talking about augmented operators. We're talking about things like inline quality checks, digital workflows, interactive SOPs. And we're talking about augmented engineers. We're talking about things like digital workflow management, instant real-time analytics, and custom no-code tables. And so really when it comes down to it, the value of augmentation can be measured in 2 domains. It can be measured from a human perspective, be it better attention, more comfortable conditions, more innovative thinking, or longer-term worker well-being, or can be measured from concrete manufacturing goals, KPIs. For example, fewer errors, higher quality, higher throughput, faster changeovers, less downtime. I think all of these things are immediately within the realm of augmentation to accomplish, to make possible on the shop floor. So the question becomes, why is augmentation necessary now? So there are 3 main reasons why augmentation is necessary. The first is the skills gap. And the skills gap refers to the disparity between the skills extant in the manufacturing workforce and the skills required to do manufacturing work. And depending on which source you consult, there's either 2.2 or 3.5 million jobs expected to go unfilled in manufacturing in the next decade. As automation keeps replacing many operator positions, manufacturing needs new skill sets like data science, software engineering, and robotics engineering, among others. And this leads to the next point, which is that although because automation hasn't taken every job, those that are left are those that are too variable or too complex for current automation technology. And in this case, it's hard to match the fine motor skills of human when it comes to very fine, complicated assemblies. And humans are more adaptable and reprogrammable than any robot on the market. They can move from task to task and learn new things and pick up new skills in ways that robots simply can't. And they're good at learning new things in a short time span. And the third, manufacturing work is evolving. And this is a natural consequence of the first 2 points. But because the skills required are different, and because the jobs left to humans are those that make workers dig deep into precisely those qualities that make us human, we now would call those adaptability, flexibility, analytical thinking, and coordination skills. Manufacturing work is changing to reflect this. So it might seem tempting in the face of a skills gap to double down on automation, but this has its drawbacks, and a lot of those come in the terms of cost and flexibility. So robots are expensive to purchase, and they're expensive to maintain, and they're expensive to scale. There are a lot of organizations that simply don't have the capital or production demand to make automation feasible. And I really like this quote, which reads like this: complexity, volume, and margin all combine in different ways to rule out the use of robots in many applications. And I like it because these three factors, complexity, volume, and margin, there's not one that's the deciding factor. They interact in different ways in a particular operation that defines whether or not automation is useful. And it's useful to think about those three ways and the way they inflect one another. And for a really long time, commentators have argued that there is an ideal balance between automation and human labor. And this is a graph from a 1993 engineering paper that argues as automation costs rise, you can see that this sort of lower rising line, the total cost of an operation rise proportionally. And this vertical line right here says optimum, represents the optimum balance between labor costs, which start out the highest, and automation costs, which quickly take over. And before this precipitous increase in both total costs and automation costs, there's this ideal place where labor costs are still significantly higher, but humans in this case are working with robots to produce the most value. And at this particular moment in manufacturing history, humans and robots working together have the opportunity to produce the most possible value. And so part of the reason that so many manufacturers are pushing for full automation comes from the fact that humans aren't perfect. They make mistakes, and then sometimes they make a lot of mistakes. And there's a lot of research that suggests that 70 to 80% of problems in a factory can be traced back to human performance. But it's not necessarily accurate to say that human error is the problem itself. Rather, most human error is attributable to system or workplace design and not to individual mistakes. And this has to do with the fact that manufacturing tools have not evolved as fast as manufacturing work. So it's still very common to see engineers walking around on the shop floor with a clipboard and a stopwatch, taking data and plotting that data by hand. There are a lot of legacy machines that haven't necessarily been brought online yet. And all of this is taking place in a context where data is necessary for work, where assemblies are more complicated, where tools just simply aren't letting workers do the best that they possibly can. There's error built into the system. And I think this is a really important point to make, and it cuts right to the heart of why augmentation is necessary, which is to say that human error is a systems problem, not necessarily a human problem. And this book comes from the Department of Energy's Human Performance Handbook. It was released about 10 years ago, and it's a really comprehensive study of human error in all sorts of high-risk industries. But the argument of the handbook is that human error can almost always be traced back to poor working systems, that the way we design our workflows and work structures builds opportunities for human error into it. So it's worth reading this quote in full. Human error is not a cause of failure alone, but rather the effect or symptom of deeper trouble in the system. Human error is not random. It is systematically connected to features of people's tools, the tasks they perform, and the operating environment in which they work. So this all begs the question: if we have a situation in which there's an enduring skills gap and full automation isn't affordable or sophisticated enough to take over at this moment, and humans need better work systems to maximize performance, how do we augment workers with the tools they need so that they can perform as effectively as possible in conditions on the modern shop floor? So in this final section of the webinar, let's look at some ways that augmentation can work in manufacturing right now. So there are a couple basic principles behind all augmented systems, and they're important to understand because they're going to be behind all of the customer case studies we'll look at in this section. So augmented systems should make moving between digital and physical spaces seamless. They should track the actions and machines of humans in real time, and they should respond to workers to help them make informed decisions. And here I'll give an example of how augmentative technologies following these principles can be integrated into workers' environments to improve productivity. It helps to put them in context with the current system. And so here we can look at paper-based work instructions. In our experience, paper-based work instructions can be hard to follow. Depending on the process, they can be over 100 pages long. They can be what we call choose your own adventure style, requiring the worker to page back and forth between different sections to find the information they're looking for. They can require double and triple checking information if a step is unclear. And they don't leave a record of correct execution. So there's no evidence demonstrating that something was performed as it says it should have been. So one of the easiest ways to augment workers is to replace paper-based processes with digital ones. And here, we're talking about digital work instructions. So these work instructions are media-rich. They can include video and images. But more importantly, they use the Internet of Things to connect the full work environment to ensure that operators are performing their tasks correctly. So for example, digital work instructions can include triggers that when an operator gets to a particular step, a Pictolite system will guide them to a particular bin that has the part that they need, ensuring that at every stage, the correct pieces are picked. Further, brake beams can interact with the operators. So as their hands move toward them, they can send signals to the work instruction app that guarantees and confirms that something was performed correctly. So all of these working together not only guide work operators toward more successful assemblies, but they provide a record that these assemblies were performed correctly. And further, there are built-in quality checks that come with these work instructions, or can be integrated into these work instruction acts that can guarantee that not only is something done correctly, but that it's up to quality as well. So IoT connected devices like scales, calipers, cameras, and others can measure and document the progression of work in progress down the line. So if humans make a mistake because they're fatigued, or don't have the attention span, or don't have the energy for the deep concentration it requires, or any of these other reasons that humans might make a mistake, these tools can help and they can provide a line of defense. They ease the cognitive load on workers by simplifying the task at hand and let them put all their mental and physical resources into what needs to be done. So let's look at a real life example of this. So this is a case of a contract manufacturer we've worked with who specializes in making complex electronics. And so the problem they faced was that their complex assemblies were guided by work instructions that didn't always have all of the information operators needed. Their production was tracked manually, and this led to a long, slow data chain. Their solution was to use digital work instructions that guided operators through each of their assemblies. In using these work instructions, throughput and quality were tracked automatically. They were displayed live on a dashboard in the factory so that everybody involved could see. And the impact of using these work instructions were immediate. So they quickly saw a 10% increase in production yield, 60% fewer assembly errors, and 5% faster build time. And it's important to note that these impacts weren't just felt by operators on the front line. These were impacts that carried over for operators and engineers. So while operators benefited from interactive work instructions that allowed them to do a better job performing their complex assemblies and adapting to this business's demand for customization, the data that these apps collected gave engineers an opportunity to iterate and make changes and optimize at a faster rate of change than they would have otherwise. So even though these are typically low volume production runs for this manufacturer, they still had an opportunity for continuous improvement in there. All right, so let's look at one more example of this. So this customer is a global medical device manufacturer, and here they use digital work instructions to guide their kitting station. At this station, operators are responsible for putting custom ordered kits for individual patients together. These could include putting any number of parts into a kit. And given the total number of parts that could go into a kit, I think it numbers into the hundreds, there are over 1 billion possible combinations. And this led to an extremely lengthy training period and a higher than desired quantity of operator errors. And you can imagine in this situation where there are so many parts that could be combined and such a high volume of kits going through, that fatigue, concentration, and boredom could all contribute to a situation in which operators performed less than desirably. So this customer built custom work instructions to guide their single-use kitting station. The work instructions used IoT to guide workers to the right parts and only the right parts, and every order was documented and photographed at the end to assure that what the work order specified actually went out the door. So that way when errors do occur, and realistically errors will probably always occur, there's documentation to show exactly where and how it happened, and it gives the manufacturer an opportunity to try to eliminate those errors further on. So in the end, they saw a 75% reduction in training time, and they had 0 unresolved shipping errors. So I hope at this point it's clear what the value of augmentation is when it comes to improving manufacturing working systems, and that by decreasing the demands we put on humans in some domains, we free them to be more efficient, accurate, and production in others. And so some of the applications I've covered here are training. So interactive training modules can capture the skills of experienced workers and help transfer them in best practices. Here you can see something like a machine changeover app, where after recording how an experienced operator changed over a machine, his or her process can be documented, captured in the app, and then transferred to future workers, so that sort of tribal knowledge that so often builds up in different departments never gets lost. And augmentation can be used to assist. And here you see a nice moving graphic of a computer vision system that's reading labels on chips, reading RFIDs, and reacting to a worker, moving them through digital work instructions in real time. And so on the engineering side, you get things like immediate production visibility. So the full shop floor visibility gives engineers the information that they need to make real continuous improvement decisions as they go based on real production data. And you get process control. So you have built-in controls that make sure that processes are performed right the first time, every time, and that there are immediate corrective actions taken and barriers put in place so that things don't go wrong in the first place. So just to recap, these are the big takeaways: that augmentation prevents human error by improving working systems. It really excels in those places where humans are prone to make mistakes, not because to err is human, but because human labor also almost always puts workers in situations that set them up for failure. So it's really about putting controls in the system that make it impossible for humans to fail. It has applications for all roles in manufacturing. So it's sort of a misnomer when we talk about the augmented operator, because it really has implications for engineers, for managers, for operators, all the way up the ladder. And it could help close the skills gap. So if manufacturing work is only going to get more difficult, and if manufacturing work is going to cause operators and every domain of manufacturing to have to stretch, these augmentation technologies can help evolve the work that they're doing and make sure that workers are trained and have the tools they need to be doing the job that they need to do. Right. So thank you everybody for listening. I really appreciate your attention. I hope this was interesting. I hope you found what you were looking for. If you still have any questions, my email is right here. So please send them in. We'd love to hear from you. And thank you very much, and stay tuned for more.